Hello everyone and welcome back. I'm Mahnur and today we will be continuing on with the chapter of AS level physics, that is kinematics. Now, so far we have understood two different approaches of understanding and analyzing different types of motion in kinematics. The first approach we understood was the qualitative approach, where we saw how we can use graphs to our advantage to better analyze and represent different kinds of moving objects. And then we had understood a quantitative analysis or approach of studying different types of motion. And this was where we were introduced with a set of very important equations that we like to call the Suvat equations. And they were as follows: V equals U plus AT, S equals half times U plus V times T, S equals UT plus half AT square, and then finally 2AS equals V square minus U square. Now what we've done at this stage is basically understood different ways we can study and analyze different types of motion. So think of these as like the tools that we will be using from here on out. So now we're well equipped in finally diving into all the variety of motions and different types of them that we will see in this chapter. And what we'll do is we'll approach it bit by bit. In other words, we'll consider the simplest examples that there are, see how their velocity time and displacement time graphs look in order to better represent these different types of motion diagrammatically as well as theoretically. Let's start things off with perhaps the most trivial example that there is out there, that is of an object that is stationary. Now, when we talk about an object that's stationary, it's basically an object that's not moving. In which case, drawing its velocity time graph might be the most trivial thing there is. It's simply a graph that looks like so. You have the velocity time graph, and there's only one graph line that you could draw that represents the velocity equaling 0 for an indefinite amount of time. That would simply be a horizontal line drawn on the x-axis like so. Pretty typical, pretty trivial. Let's see what the displacement time graph looks like. And for this, we'll have to do a little bit of recalling first and foremost. Now here we know that we have displacement on the y-axis, time on the x-axis, well and good. But then we remind ourselves that for a displacement time graph, the gradient represents velocity. So if we expect velocity to stay 0, that means the slope of whatever graph line we draw must be 0 as well. And there's only one graph line shape that we could possibly draw such that it has no rise or no fall. That's basically a horizontal line. So I could very well draw a line that's similar to the one I drew previously, like so, on the 0 line. But then if I wanted to draw a horizontal line, I could have drawn it over here. Suppose this line I draw is 10 meters above the x-axis. Now I ask you this: do these two graph lines represent the same stationary object, or is there some kind of a difference between the two? Think about it for a moment. Well, it turns out that while these two graph lines do represent objects that are stationary, they're actually two different objects entirely. Instead of objects, think of them as two observers or two friends of ours. Let's say the red line represents the graph line of our friend Tufi right here. Now, Tufi over here is basically standing on the 0 point, or think of it as like the origin or the reference point. And they're standing stationary at this point. We call it a reference point only because all other displacements are being measured relative to this. So in that case, imagine Tufi standing here stationary. The purple line, suppose, is Dr. Sal, that's standing 10 meters away from the reference point, meaning they're standing 10 meters away from Tufi, somewhere over here. Let's not forget his glasses. And that's our Dr. Sal. So now you can see that when it comes to two horizontal lines drawn on a displacement time graph, both represent observers that are stationary. The only difference lies in the position. So there's a difference in position that we must account for. Great. Now let's increase the complexity a little bit. Now, after having looked at what a stationary object looks like, now let's see what an object moving with constant velocity looks like. Now, since we're dealing with an object that is moving with constant velocity, we immediately have to keep in mind that we're expecting velocities to stay non-zero. Even here, the velocity time graph is quite simple to draw. You have on the y-axis velocity, and on the x-axis you have time. Now here too, let's see how can we draw the graph line over here. Now we know that, and we must remind ourselves that for a velocity time graph, the gradient represents acceleration. So if velocity is constant, that basically means velocity is not changing. And when velocity is not changing, there can't be any rate of change of velocity either, in which case acceleration ends up being zero, which in our case, especially in this case of a velocity time graph, means that the slope here should be zero. So once again, we must draw a horizontal line here as well. And here too, you can place the horizontal line above the x-axis or below, and we'll find out that they mean two different things entirely. Suppose one graph line is horizontal above, and let's suppose this is at 10 meters per second. And let's suppose this is the graph line of our trusted friend Tufi. And let's suppose our trusted scientist, Dr. Sal, his constant velocity is on the negative side of the y-axis. And let's suppose it's minus 10 meters per second. Now, what does this mean physically? Well, it turns out that this time we remind ourselves, in fact, that velocity is a vector. So the negative sign merely represents an opposite direction. So if let's say Tufi is moving with 10 meters per second towards the right, Dr. Sal, on the other hand, is moving towards the left with the same amount of velocity. Here the position or the starting point doesn't really matter. What matters is that they're moving in opposite directions with different values of velocity. Great. Now let's see what does constant velocity look like on a displacement time graph. Now for a displacement time graph, we remind ourselves that you have displacement on the y-axis, time on the x-axis. And here we remind ourselves that since velocity is constant and non-zero, we expect the gradient or the slope of the graph to also be constant and stay non-zero. Now there's only one graph line that we could possibly draw such that it has a constant slope. That's basically going to be a straight line. Now even here, I could draw a variety of straight lines. I could draw one that's passing through the origin, or I could draw one that's perhaps starting a few meters above the origin. Suppose where the origin starts at 0, the purple line starts with 10 meters, let's suppose. Now once again, let's see how things look physically. You'll have once again level ground. Let's suppose the red line represents the motion of Tufi standing or starting their motion at the reference point of 0. Basically, what this means is that Tufi here is moving with constant velocity, but they're starting their motion from the 0 point. Dr. Sal, on the other hand, is also beginning to move with constant velocity. However, Dr. Sal is going to start his motion 10 meters away from Tufi, standing at the origin. So that's Dr. Sal, also ready to move in the opposite direction. Now, this is where we find that the slope is constant and it's staying positive. But straight lines like these could also very well have negative gradients. What would a graph line like that look like? So let's suppose the graph line is this instead. Now how would the graph shape look like? Now how would this look physically? Well, think of this as a third observer who is standing first and foremost 20 meters away from the reference point. So we could extend this line a little bit and draw our third surprise guest 20 meters away from Tufi standing on the reference point. Now notice how as time goes on, the graph line, this green one, seems to be approaching the x-axis. In other words, it's approaching the origin, which is to say that this green observer is now moving in the opposite direction and is approaching towards the reference point at 0. And so we find that in this case, negative gradients means that more objects or observers are moving in opposite directions. And this is a very important point to keep in mind, that negative gradients or negative slopes means that the object or the observer is moving in the opposite direction. And since the gradient is constant, we expect the velocity to stay the same regardless. Alright, good. So we've looked at the first most trivial case, and then we looked at the next simplest scenario of constant velocity. Now let's increase the difficulty even more and now talk about objects moving with constant acceleration. Now, throwing around the word acceleration can be quite daunting in the beginning, so I would like to take a quick detour and first show what an object moving with constant acceleration might look like physically, and then see what its graph looks like. So let's understand this physically first by considering the following level ground. And let's suppose we have a trolley that's starting its motion from 0 seconds. And let's say they're starting off with 0 velocity. And now we will basically let this trolley move and see what velocity value does this trolley attain at 5-second interval. So imagine us taking pictures every 5 seconds and see what value of velocity the trolley has. Now let's suppose after the first 5 seconds go, the velocity this object attains is 10 meters per second. Then another 5 seconds, 20 meters per second. Another 5 seconds, 30 meters per second, and onwards. Let's see what value of acceleration do we evaluate at each time interval. At the first stage, we'll basically use our formula for acceleration, final velocity minus initial velocity, in which case we get 10 minus 0 divided by a 5-second time interval 5, and we arrive at 2 meters per second square. Now let's evaluate the next acceleration value. Here we get 20 minus 10 divided by the same 5-second interval. We get once again 2 meters per second square. And now once again we do it here, A3, 30 minus 20 divided by the same 5-second interval, and we get 2 meters per second square. What's remarkable here are two things. First of all, we find that there's a constant increase in velocity of 10 meters per second after each equal interval of time, which has led us to further conclude and in fact prove that with increasing time and with the passage of time, the acceleration value itself does not change. This is basically what constant acceleration is all about. We can categorize it as or describe it as the increases in velocity staying constant for equal intervals of time. Either that's how you could describe it, or you could describe it as the kind of motion wherein acceleration stays constant for equal intervals of time. For equal intervals of time. Right? Now that we've understood what constant acceleration means physically, we can now better understand how we can draw the velocity time graph right here. So we'll have this velocity on the y-axis, time on the x-axis, and now let's take things step by step. We know in the scenario that we just drew, that acceleration was positive throughout. So we do expect the slope itself to also be positive. Moreover, we saw that acceleration is constant. It's not changing its value with respect to time. Which means, in this case, since the slope of a velocity time graph does represent acceleration, we expect the slope to be constant as well. And once again, there's only one possibility over here, that is a straight line. Now, if I were to draw the straight line starting from the origin, it would look something like this. And what this means physically is that our observer, perhaps Tufi, is starting his motion from rest at 0 meters per second, and then the velocity gradually increases by a constant rate. If you had Dr. Sal, perhaps he was already moving by the time you started your stopwatch, in which case at time t equals to 0, there might be a non-zero value of velocity, in which case the graph line of Dr. Sal could very well start from above the origin. But they both represent constant acceleration regardless. Now, the existence of a positive slope implies that there could very well be a graph line that could represent a negative slope. That's basically when you consider a decrease in velocity instead of an increase. That's where we encounter what we call deceleration. So let us describe deceleration first through constant deceleration. Once again, we'll consider our same trusted trolley. Let's suppose the trolley is starting their motion from 0 seconds. We'll once again take the same approach of taking snapshots every 5 seconds of this trolley. And we'll basically see what value of velocity does this object contain or carry. Let's suppose the trolley was already moving as we started our stopwatch, in which case let's suppose it started at a value of 50 meters per second. And then 5 seconds later it drops to 40. Then 5 seconds later, 30. And 5 seconds later, 20, and so on and so forth. Now let's see what values of acceleration do we get for each equal interval of time. For the first time interval, we get 40 minus 50 divided by 5, giving us minus 2 meters per second square. That negative sign represents a decrease in acceleration, and we'll see that for all these two other intervals that we'll calculate. For the second interval, we have 30 minus 40 divided by 5, giving once again minus 2 meters per second square. And for the third interval, 20 minus 30 divided by the same 5-second interval, giving you once again minus 2 meters per second square. Notice how, number one, there's a decrease in velocity occurring. Not only that, but the decrease in velocity for each interval of time just so happens to be kept constant. And we see that the value of this negative acceleration, which is precisely what we call deceleration, it's staying the same. So now we categorize constant deceleration as the kind of motion wherein decreases in velocity stay constant with equal intervals of time. Intervals of time. Another way to categorize constant deceleration is the fact that the value of deceleration, or you could even call it negative acceleration to be precise, that is what's staying constant with equal intervals of time, right? Intervals of time. With this physical understanding, we are now ready to draw what its graph will look like, specifically its graph on a velocity time graph. We have velocity on the y-axis, time on the x-axis. And now this time we clearly expect throughout the acceleration to stay negative, which is why the slope of a velocity time graph should also be negative. And since it's constant, we expect the slope to be constant as well. So you want to draw a graph line that has constant gradient or slope while also having a negative slope. The only kind of graph line that we could possibly draw is one that is tilted downwards in a straight line. Right? Now that we've dealt with both kinds of constant accelerations, positive and negative, now we're ready to dive into a possible kind of motion wherein acceleration is very well subject to change. This is where we dive into what we call variable acceleration. So variable acceleration, as the name suggests, is basically the kind of motion where acceleration is no longer constant. While of course there's a variety of ways acceleration could definitely change, we'll be studying two different kinds. There will be a kind where acceleration increases with time. That's what we call increasing acceleration. And then there's another kind where acceleration continues to decrease, and that's what we call decreasing acceleration. It's good to understand what each of these mean physically first, just for a better understanding, especially when it comes to concepts, and then we'll see what their velocity time graphs look like. Now, increasing acceleration, as tricky as it sounds, is actually quite straightforward to draw. And we'll actually draw it using our trusted trolley. We'll take our trusted trolley and take snapshots of it after every 5-second interval. So 5 seconds, 10 seconds, 15 seconds. And then we take snapshots and see what value of velocity does it have after each 5-second interval as it goes forwards. Suppose it starts its motion from 0 velocity, and then starting from rest after 5 seconds, suppose its velocity shoots up to 10 meters per second. Then it shoots up to 30 meters per second. And then it shoots all the way up to a sudden 80 meters per second. Clearly we see that there is an increase in velocity, alright, but the increases in velocity, or those changes in velocity at each interval of time, seems to be increasing. First there's a gradual jump from 0 to 10, then a 20 unit jump from 10 to 30, and then 30 to 80, a 50 meters per second increase. We can quantify this sudden change through calculating the accelerations for each 5-second interval. For the first 5-second interval, we get 10 minus 0 over 5. We get 2 meters per second square. For the next 5-second interval, we get 30 minus 10 divided by this 5-second interval 5, and we get 4 meters per second square. And then we have the third 5-second interval, 80 minus 30 divided by 5. That will be 10 meters per second square. See how the value of acceleration itself is increasing as well, meaning the object is not accelerating uniformly, but rather its acceleration continues to increase, which is obvious from the fact that the changes in velocity also increase with time. This is precisely what we call increasing acceleration. We describe it as the kind of motion wherein increases or changes in velocity increase themselves with equal intervals of time. Or you could also categorize it as the kind of motion wherein acceleration increases with time. With equal intervals of time. Right? Now let's see what the graph of an object moving with increasing acceleration will look like. Specifically, the velocity time graph. Velocity on the y-axis, time on the x-axis. You have 0 here. Now, throughout we do expect the gradient to stay positive, as we saw in our physical example before. So we expect the slope that we draw to also be positive throughout. But the acceleration is not constant anymore, but rather is increasing, meaning whatever graph line we draw must have a slope such that it is increasing. So this is definitely going to be a curve because it's a straight line. Oh, it's going to be a curve because a straight line has a constant gradient or a constant slope, and curves tend to have slopes that change. What kind of a slope should we draw then? What kind of a curve should we draw? Well, in this case, we draw a curve like so. This might seem like a random guess, but we can actually justify this choice. Again, we remind ourselves that we want a curve whose slope increases with time. So with the gradual passage of time, we want the curve to get steeper basically. So notice how for each point in time I draw a tangent and see how the tangent seems to be getting steeper and steeper, which means that this graph line has a slope that is definitely increasing with the passage of time. And so this red shape is perfectly valid. Great. Now that we have a good understanding of what increasing acceleration looks like, it's easy to understand what decreasing acceleration will look like. And let's draw that next. Here too, we'll resort to our trolley. Right here. We start its motion from 0 seconds. After each 5-second interval, we'll take its snapshot and see what value of velocity it attains. This time, let's suppose here too, it starts its motion from rest, meaning 0 velocity. And let's suppose the velocity actually shoots up to 50 meters per second first. Then it increases to a measly value of 80 meters per second and then a gradual 85 meters per second. Now here we can't say that the object is slowing down because the velocity is definitely increasing to larger values than before. But notice how the increments are getting smaller and smaller. Once again, we can quantify this better by calculating values of acceleration for each equal interval of time. Let's take the first interval, where we get 50 minus 0 divided by the 5-second interval 5. Here we get 10 meters per second square. Then you have the second value of acceleration, 80 minus 50 divided by 5. We get 6. And then finally, 85 minus 80 over 5 equals 1 meters per second square. Notice how even though the object is definitely speeding up, we notice that the increments in velocity keep on decreasing, and that's symbolized by the fact that with the passage of time, the value of acceleration, albeit being positive, actually ends up decreasing with time. This is the essence of decreasing acceleration. It's described as the kind of motion wherein acceleration is decreasing with equal intervals of time. But you can also describe it as the kind of motion wherein the decreases in velocity in themselves are decreasing with equal intervals of time. Right? And now once again, let's go back to the velocity time graph and see how we can draw this graphically. Now here too, we expect the gradient to stay positive because the acceleration is positive. So whatever graph line we draw must have a slope that is positive. But then this time, the value of acceleration should be decreasing, which means the slope for a velocity time graph should also be decreasing. For such a kind of graph line, this too is going to be a curve. But it won't be a curve like we had drawn before. It's going to be a curve that will be drawn instead like this. Once again, this might seem like a guess, but it's perfectly valid here as well. Because if you look carefully, with the passage of time, we find that the graph line is getting less steep, meaning its slope is getting smaller and smaller. To confirm this, we can draw tiny tangents at each point in time and see how the tangent's own slope is getting smaller and smaller, or is getting shallow, which justifies completely that this red curve works perfectly well for an object that's moving with decreasing acceleration. Great. So we have covered variable acceleration, specifically two types. Just to kind of summarize where we are. We looked at what the graphs for increasing acceleration look like, wherein the value of acceleration is increasing and stays positive. And then we looked at the other scenario of decreasing acceleration, where the value of acceleration is still positive, it's not slowing down, but the value of acceleration itself, while being positive, is decreasing with time. But at this stage, we do know that wherever there's positive acceleration, there is a possibility of there being negative acceleration or deceleration, which means increasing and decreasing accelerations have their negative counterparts as well. You have increasing deceleration as well, and moreover, you have the possibility of decreasing deceleration. Now I know at this stage it seems like we're just adding more and more complicated things to the list of different types of motion, but this isn't all too difficult. In fact, I want you to give this a try yourself, pause this video and see how you can sketch velocity time graphs for both increasing deceleration and decreasing deceleration, and then we'll draw them here together, starting now. Well, now let's cross-check whether your answer is correct or not. For increasing deceleration, you expect the graph line itself to have a slope that is getting negative and is also increasing, because for a velocity time graph, remember that the slope represents acceleration. So in this case of increasing deceleration, you expect acceleration to be negative and increase with time, meaning the slope should behave the same. So the slope should be negative, meaning it should be a graph line dipping down, and it should be a curve in such a way that its steepness increases as time goes on, which would be a nosedive kind of graph line like so. Now let's see what the decreasing deceleration graph looks like. Here, for decreasing deceleration, the name suggests that the value of deceleration should decrease with time, meaning acceleration should be negative and should be decreasing. Meaning whatever curve you draw here should have a slope that stays negative first and foremost, but should decrease with the passage of time. That would be a shallowing kind of graph like so. Right? Great. Now, before we wrap things up, it's important to notice something at this stage. Notice how I have yet to draw any kind of a displacement time graph for all these different types of accelerations. Why do you think that is? Why is it that I have just somehow forgotten to mention what a displacement time graph looks like for different types of acceleration? Well, it's not a matter of just being absent-minded, but rather it's a matter of displacement time graphs being graphs that don't give us too much information about the type of acceleration that the object is undergoing. It's just a fact that displacement time graphs don't really give you too much information. The most that a displacement time graph can tell you is whether or not the acceleration is positive or whether or not the acceleration is negative. Meaning, a displacement time graph alone at least can't really tell you whether whatever acceleration the object is undergoing, is it constant, is it changing, is it increasing, or is it decreasing. The most it can tell you is whether the object is speeding up, which is what we call acceleration, or whether the object is slowing down, which falls under deceleration. But despite these limitations, we are of course welcome to understand each of these graph shapes themselves. So let's go over this finally. Now we know that an object that's accelerating, meaning has positive acceleration, means that its velocity is increasing. It doesn't really matter how it's increasing as long as it's increasing. And if it's increasing, that means for the displacement time graph where the slope does represent velocity, the slope should also increase. Now let's see what things look like for deceleration, where we have negative acceleration. This is where the object is slowing down, meaning velocity is decreasing. Under that scenario, for a displacement time graph, the slope must be decreasing. Now immediately I bet it's easy to guess what kind of a graph line you could draw. For a displacement time graph representing acceleration, the curve should be such that, oh my bad, the origin should be here, and this should be the label time. For a graph line representing acceleration on a displacement time graph, the shape itself should be a slope with increasing gradient or increasing slope, which would be something like this. And if you have someone like Dr. Sal who likes moving in the opposite direction, then you would prefer the graph line to be negative to represent motion in the opposite direction, but it would slope in such a way that it gets steeper with time. And if you had deceleration, this is where the slope would be decreasing definitely, and in a way that you can draw the curve like this in one direction, and if something is moving in the opposite direction, then the slope would be negative, but the gradient should be such that it keeps on decreasing with time. So something like this. Once again, I remind you that these purple graph lines represent motion in the opposite direction. So this is worth mentioning, and I'll in fact quote it right here, that both of these purple lines represent motion in opposite directions. But they still nevertheless represent acceleration in this case and deceleration in this case. Great. Now we have finally understood the huge variety of different types of motion that we can have around us, and especially in AS level physics. Now let's see how we can apply a few of these tidbits of information on some kind of practice question. So let's start. So here we have the following question. When a car driver sees a hazard ahead, she applies the brakes as soon as she can and brings the car to rest. The graph shows how the speed v of the car varies with time t after the hazard is seen. Which graph represents the variation with time t of the distance s traveled by the car after the hazard has been seen? So we basically have to pick one of the following distance time graphs that relate well with the above drawn velocity time graph. Here we'll have to remind ourselves of two important points. Number one, the slope of a velocity time graph represents acceleration, and the second thing being that the slope of a distance or displacement time graph represents velocity. So we'll basically be using both of these pointers to link from the first graph drawn above to one of the options given below. Before we can do that though, let's actually interpret this larger convoluted kind of a graph into two distinct sections. one horizontal line highlighted in yellow and one line that's tilted downwards highlighted in green. Let's look at the yellow portion first. Now for this yellow portion right here, I'll note it with an arrow. We can see here that the slope of this portion of the graph is 0. And for a velocity time graph, that would mean acceleration is 0, which is to say that from 0 to t1 seconds, the object is moving with constant velocity. On a distance time graph, that would mean you have a constant slope from 0 to t1. So we can cancel out option A, for instance, because here we see that the slope is 0, not constant. So we're left with B, D, or C. Now, for this, to now see which one of B, C, or D can be the answer, we'll now study the green highlighted portion. For the green highlighted portion, I'll draw the arrow to refer to it here. Here we see two things about the slope, and I'll write them down individually. The first thing I see about the slope is that it's constant, but then I also see that the slope is negative. Let's analyze these individually. When the slope is constant, that is to say that acceleration is non-zero and constant, meaning the velocity is no longer constant. In fact, the velocity is definitely changing. The velocity is changing. And when the slope is negative, that means acceleration is negative as well, meaning not only is it constant, but it's referring to a car that is actually slowing down. So the velocity is decreasing as well. So when it comes to choosing which graph to pick from B, C, or D, we can immediately first understand that when the velocity is changing, you expect the gradient of whatever graph you choose to also change as well. So it can't be a straight line like we see here in option B. So once again, we cancel out D. Now we're left with either C or D. You want to pick a curve such that its gradient keeps on decreasing. That would relate with the velocity decreasing with respect to time from t1 up to t2. For that though, we can basically use the concept of tangents to figure out whether the curve drawn in C works or D. For C, we can see that with time, the slope is getting smaller, whereas for option D, we see that the slope is actually getting steeper. So D is actually going in contradiction with what we want there to be, that is a decrease in velocity. So D can't be the option, and so the only option that works is C. So I hope up to this point, an understanding of the different types of motion and how you can use graphs to analyze them is something that you're quite comfortable with. Thank you.